Hi class, welcome to our module 2. So for this module we will be discussing about strain. So for module 1 we were able to discuss what stress is. So we defined that stress is a force applied on a certain unit of area. So for module 2 we will be discussing about strain. Okay, so as you can see in your screen, we have here an assorted of tensile test specimens. So the tensile test is a standard procedure for determining the mechanical properties of materials. An important material property is the stress-strain diagram. So this is very important specifically for steel materials, steel-related materials. Okay, because we can determine the tensile stress, the actual force, which is compression and tension. So for tension, we can determine the tensile strength of the material using a tensile test. Okay. So here we begin our study, the relationship of stress and strain to each other, which defines the mechanical property of a material, the knowledge of which is of the utmost importance in design. Okay, so later on we will be discussing why is it very important for us to determine the tensile strength of the material with respect to the stress strain diagram. Okay, you will understand how stress can be related to strain by using experimental methods to determine the stress strain diagram for a specific material. The behavior described by this diagram will then be discussed for materials that are commonly used in engineering. Also, the mechanical properties and other tests are related to the development of mechanics of materials will be discussed. Okay, so we have here the normal axial or the normal, which is also an axial strain. Okay, so when we say normal strain, it is perpendicular to the cross-sectional area. Okay, so we must formalize the definition of normal strain. We begin by considering the elongation of a prismatic bar. So for example, you have here your material. This one is still undeformed. Ibig sabihin, wala pa tayong loadings na ina-apply. Now, once there is already a loading, and that loading is applied here at this part, it will be going to pull this material, then therefore there will be an elongation. Okay, and that is what we call the strain, yung elongation, yung deformation, yung change. So the change in the length divided by the total length, therefore that is your strain. Strain is a unitless ratio. It is the ratio between the elongation or the deformation with respect to the original length. Okay? And if the deformation is not uniform, we must define the strain at a point. In figure 2.1, we let O to be a point in the bar located at a distance x from the fixed end to determine the actual strain at point O. Okay, so we consider the deformation of an imaginary line element OA of length delta x that is embedded at the bar at O. So delta x here is the change in the length. So denoting that the elongation of OA by delta D, we define the actual strain at point O as delta L deformation divided by delta x is equivalent to the change in the deformation with respect to dx. Again, this equation is good if our cross-sectional area is not constant. Okay, so the tension test. So the strength of material depends on its ability to sustain a load without undue deformation or failure. It is very important for us to determine the behavior of the material when will it be on the plastic state or the elastic state. Okay, later on I will be discussing what is elastic state and what is plastic state. So ang gusto natin mangyari, if we are going to apply load on this material, at what point will this material fail? At what point will this material be on still on the elastic state or the plastic state na? Okay, so with the help of the universal testing machine, so you can find this at H 104, I think, on the first floor of Otohan. Don't worry if you we will be having if we are already going to have our physical classes on the first sem for your construction CMT, construction and testing materials subject. You will be meeting this equipment. So this equipment is very important because it is helping us determine the strength of the material at failure. Okay? Bakit hinahanap natin yung strength ng material at a yielding point or at the failure point? Kasi yun yung mga properties na kailangan natin in designing. Okay? So these data are then converted into stress. So ang mangyayari dito sa ating universal testing machine, ilalagay natin dito yung ating specimen, then unti-unting hinihila yan. Hinihila ng universal testing machine pataas. And the load is in kilograms. Take note, yung kilograms na yan, it is a force. Okay? So, to convert that, meron naman area yung ating cross-sectional area yung ating steel bar. Then from there, we can get the stress. Okay? So, the strain is computed from the deformation divided by the total length, where D is the elongation between the gauge mark. So, lalagyan natin ng mark yung ating bars. Then, from there, we are going to determine the elongation divided by the original length. So, from there, we can now determine our strain. Okay? The result of which are based on the original area and the original gauge length are referred to the nominal stress or the nominal strain. Okay? So, ito yung sinasabi ko sa inyong stress-strain diagram. So, habang itong machine natin, itong universal testing machine, habang paunti-unti yan na hinihila niya paunti-unti on both ends yung ating steel bar. So, kunyari, imagine niyo ito nakatayo. Hinihila dito, and dito, sa baba, naka-fixed. Okay? So, hinihila itong steel natin. Of course, there is a force applied, nag-elongate yung material natin. So, habang nag-elongate yung material natin, this is the behavior, linear. Okay? So, that linear yung relationship natin. So, at the point of the yield point, yung sinasabi nating yield point or yield strength, ibig sabihin, hanggang sa point na to, pag tinanggal mo yung load natin dito sa ating steel bar, babalik sa original form or sa original shape yung ating material. Therefore, it is still in its elastic state. I repeat, pag tinanggal mo yung load, yung force P na yan, and nandun ka sa yield point, umabot ka sa yield point, at tinanggal mo yung load natin, babalik sa original form yung ating material. Okay? But, ayun yung tinatawag nating elastic state. Ibig sabihin, pag tinanggal mo yung load, babalik siya sa original. But once it passes through the yield point, lumagpas na siya sa yield point, dediretso na siya dito, nandito na siya sa kanyang plastic state. Ibig sabihin, when we remove the load, the deformation on your material would already be permanent. It is irreversible. Hindi na natin pwedeng ibalik sa original state. Okay? Then when we say ultimate strength, ito yung pinaka-capacity ng ating material. This is the highest strength or the highest load that it can carry. So pag lumagpas pa dyan yung load na bubuhatin ng material natin, definitely it will fail. That's why it is called the true rupture strength. So for example, the ultimate strength is around, for example, just an example, around 100 kilograms. But the load that it is going to carry is 101, therefore it is already going to fail. Okay? And the normal rupture strength, ibig sabihin, pag na-reach na yung ultimate strength, of course, mag-elongate pa rin yung material natin, pero bumababa na yung kanyang kayang i-carry na load. Then, until such a point na maputol. Pag naputol na yung material natin, then that's the normal rupture strength. Okay? So, that is our stress-strain diagram. Okay? So, the linear relationship between the stress and the strain is what we call the Poisson. That is what we call the Poisson ratio. No, it's not the Poisson. It is the Hooke's law. It is the Hooke's law. Sorry. So the linear relationship between the stress and the strain is what we call the Hooke's law, wherein the stress is equivalent to the modulus of elasticity of the material times the strain. Okay? Remember, for Hooke's law, we can only use Hooke's law if it's still in its elastic state. But once it is already in the plastic state, limited na yung paggamit natin sa Hooke's law. Okay? So normally, for a steel, yung steel bar or yung any steel, no? Normally, the modulus of elasticity of steel is 229 times 10 raised to 6 Pascal per square inch, or it is 200 gigapascal. Okay? Note that Hooke's law does not apply beyond the entire diagram. Its validity ends at the proportional limit. Beyond this point, stress is no longer proportional to strain, because the relationship is no longer linear here in the plastic state. That's why we can no longer apply here the Hooke's law. Okay? So for elastic limit, we have high carbon steel. Mas mataas yung kanyang stress strain, mas mataas yung kanyang failure without significant yielding. Cast iron, medyo mas mababa compared sa high carbon steel. Aluminum, mas mababa sa cast iron. And concrete, of course, mas mababa. Okay? Take note that concrete is very weak in tension, but it is very high in compression. Okay? But of course, there's still we still get the stress strain diagram, of course, in relation to compression. Okay. So elastic limit, material is said to be elastic if after being loaded, the material returns to its original shape when the load is removed. Yield point, the point where the stress strain diagram becomes almost horizontal, is called the yield point. And the corresponding is known as the yield strength. So if we are going to observe, or let's try to zoom in. Ayan, pag umabot na siya sa point dito, almost horizontal na yung point na yan, ibig sabihin, yan yung ating yield point. And when it starts to go up, then we are already entering the plastic state of the material. Okay? Ultimate stress, the ultimate stress or the ultimate strength, as it is often called, is the highest stress on the stress strain curve. It is the highest stress, ibig sabihin, yun yung pinaka-maximum na kayang i-hold ng ating material. So, for the rupture stress, doon na magbe-break yung ating material. Okay? The true rupture strength is larger than the ultimate strength. However, the ultimate strength is commonly used for maximum stress that the material can carry. Okay? So, ito yung ginagamit natin sa design. Ultimate stress and yield stress. Ultimate strength, yield strength. Yan yung mga ginagamit natin sa design. So, actually loaded bars. So, for figure 2.7 shows a bar of length L. So, we have here a bar length L that is loaded with an actual tensile force P. And we have here the cross-sectional area, which is A. So, we assume that the stress caused by P is below the proportional limit, so that the Hooke's law, S, is the stress is equivalent to the strain times the modulus of elasticity is applicable. Because the bar deforms uniformly, so since it is in normal strain or normal stress, the deformation from a certain point will be the same as the deformation all throughout this cross-sectional area. Okay? So, the actual strain is equivalent to the deformation divided by the total length, which upon substitution into the Hooke's law yields the stress is equivalent to the modulus of elasticity. Substituting the formula of the strain is equivalent to the deformation divided by the total L. Therefore, we have this equation. The deformation is equivalent to the stress times the length over the modulus of elasticity. But we know that the stress is equivalent to the force over area. Therefore, we can have this as our working equation. So, the deformation is equivalent to PL over AE. So, kindly memorize this formula. Okay? If the stress or strain in the bar is not uniform, it is changing, the cross-sectional area is changing, okay, then the elongation at the bar can be obtained by integration of P dx over EA from 0 to the length L. Okay? So, the notes on the computation of deformation. The magnitude of the internal force P must be found from equilibrium analysis. I repeat, the magnitude of the internal force must be found in the equilibrium analysis. So, we need to do our equilibrium analysis. So, positive for tensile, and of course, positive for elongation. If it is compression, therefore it is negative. If our material shortened or it was compressed, therefore it is negative. Okay? Be careful with your units, consistency of units in your formula. As long as the actual stress is in the elastic range, the elongation of the bar is very small compared to its length. I repeat, pag nasa elastic state or elastic range pa yung elongation natin, sobrang liit lang yan. Compared sa plastic na, it is very evident, malaki na siya compared sa original state. Okay? So, that's for part 1 for the problems that would be handwritten.